Good afternoon. Welcome to another lesson. And it's a beautiful day in Kansas City. Let's see if I can show you. Oh, wrong way. Super nice out. It's like 60 degrees, so I'm going to be thankfully I'm off work. But I spent my morning working on a new lesson, and it's about rainbows. Rainbows are something that they're cool, but it's funny because you think it's like a distinct thing placed in the sky. And I always kind of wondered, what really is a rainbow? And I studied it and put together this short lesson about rainbows. To start, though, I think it's cool to tie mythology about things to current science. So I'm going to read a super short little story of the origin of the rainbow from a tribe off the coast of California. So thankfully I'm using my favorite books I've been reading by Richard Dawkins, and it talks about this myth. These are the great pictures. Unfortunately, these are what I drew. My California looks pretty good, but that's Kaylee as the Earth Goddess. But yeah, so I guess I could hold this up and read it. But anyway, okay. So the reason I picked this myth is because it happens on Santa Cruz Island, which is off the coast of California by Los Angeles. And Catalina Island is right here, and I lived there for 6 weeks. So it's kind of cool to see what people thought happened way back in the day, and I was on that same land. So here's the story. Okay, so the Chumash people believed that they were created on their island. Here's their island. From the seeds of a magic plant planted by the earth goddess Hutash. So Hutash planted this plant, and all these little people came from it. And Hutash was married to the sky snake. Don't ask me why she married a snake. That's kind of weird, but the sky snake is reminiscent of the Milky Way. Okay? So the people of the island became very numerous, too noisy for the goddess Hutash's comfort, and the racket kept her awake at night. But instead of killing them all, like the Sumerian and Jewish gods, Hutash was kinder. She decided that some of them must move off Santa Cruz onto the mainland, where she wouldn't be able to hear them, and so she made a bridge for them to cross by. And the bridge was, yes, a rainbow. Woo! So, this one's even funnier. She made a bridge. Here's their little island. And they go, woo, over the island to California. And ironically, in this myth, it says some people decided to look down, and they fell into the water and turned into dolphins. Maybe. But, so, that is one of the myths of the rainbow. This. Now, to start talking about rainbows and to get into the scientific aspect of it, we're going to talk about lights and white lights and what white light is. I don't really need to thumbtack these, but okay. So Sir Isaac Newton is probably one of the best scientists ever, and he was the first to subdivide a white light using a prism into the component colors. White light is a mixture of all of the colors, okay? That's all it is. It's pure color. So, what Isaac Newton did in 1650 was he got in his office and made it real dark, and he drew the curtains. And he let a little slit of white light pass through the window and hit a prism. A prism is basically like a glass triangle. The prism, in turn, produced a rainbow. It separated the colors of the white light. So when white light passes through a prism, it gets refracted, and it's broken up into a rainbow. So what is refraction? The definition is the change in direction of a wave due to its change in medium. Now, light is a wave, okay? And a medium is basically the environment that the light passes through. So in the case of the prism, what happens is the medium is air, it's traveling through air, then it hits glass, which is a brand new medium, and because of that it gets refracted. So basically the light wave is bent when it changes mediums. And you can see this in water too, like a straw in your Coke or an oar in the water, that the light hits the object in the air, change of medium equals a refraction, a bend in the angle, which changes how you see something. And depending on what color is being refracted, the angle of the bend will be different. So, like red light bends shallower than blue light, so the angles are different, the light shows. So that's just a little gist. I wish I had a prism, but I don't, and there's no rainbow outside, so you can only close your eyes and picture what's going to happen. Now here's an even funnier artistic drawing. Woo! Alrighty. So, this is, you're probably thinking, what does a prism have to do with a rainbow? And this is where we're going to talk about it. To see a rainbow like this very handsome stick figure, you have to have the sun behind you. You cannot see a rainbow unless the sun is shining behind you. The sun provides that white light that you need. So here comes the white light, and as you can see, it's raining. And this is a normally large raindrop, but each raindrop acts almost as a little prism. The shape's different, it's circular. So what happens in the raindrop is different refraction-wise than what happens in a prism, but it's the same concept. So white sunlight comes and it'll hit a raindrop. It'll hit the top, and because it's changing mediums from air to water, the light is broken, it's refracted, it hits the back, here we go, it hits the back of the raindrop, and then goes to the front, and then what happens is that changes mediums again, travels through the air, and depending on the wavelength and the angle of the light, like say it's red light, so it bends differently, the red light will reach your eyes. But you never see a full color spectrum, a full rainbow from just one raindrop. Each raindrop, depending on where it is in the sky, and kind of just depending where it is in the sky, will provide one color. And if you think about it too, it's constantly raining, so it's recycling. That's why a rainbow seems to stay stationary, because it's constantly being recycled by rain. Okay? Talk about that one. Let's get my next. This one's the best. So here we have a Royals player, and he's looking at a rainbow. Again, the sun is behind him. And we have 4 raindrops placed here, A, B, C, and D. The same science that we talked about happening in this raindrop is happening in these other raindrops. But because of the position and where they're located, and because of the differences in refractions from where you're standing, each raindrop and each layer of the rainbow provides that specific color. That is what you see, that one color from that one layer hits your eyes, and you get a rainbow. So each individual raindrop reflects or refracts a specific color of the color spectrum, which hits your eyes and hits your eyes, coloring in a rainbow. There we go. And it's interesting to think of waves, or of light as a wave, because it's just light, but it is a wave. And we're going to end it by talking about wavelengths. And this is a really interesting fact that I always like to think about to make the world more magical, if you think about it. So here is the wavelength chart. Okay, so wavelengths are basically the length. Give me 1 second. Alright, we will use the back of this one. So there are different kinds of wavelengths. The wavelength is the distance from crest to crest or trough to trough. And it's denoted by lambda, but I don't know. There we go. That's lambda. Okay, so this is a symbol for wavelength. It's a Greek letter. But wavelengths are the distance from here to here. So you have super fast wavelengths, medium wavelengths, and large or long wavelengths. And they're really actually super small if you think about it, but comparison, they're a little bit different. Aha, here we go. So when we got to the really short wavelengths, the really quick ones, those are gamma rays, and they are 10 to the negative 14 meters. That's the difference between, so it's pretty close. So you go from gamma rays and you go to X-rays, ultraviolet, and then right here, this really small region and this vast thing of wavelengths, that's visible light. That is what we can see. It provides the colors, the rainbow. And they go from 400 nanometers to 700 nanometers. So you have violet, has a smaller wavelength than red. Really not that big of a difference. Following visible light, you have infrared rays, radar, FM like your radio, TV, shortwave, and AM like your radio. If you look at this chart, you can see that there is so much out there that we cannot sensibly see. We can't see X-rays. We can't see ultraviolet. We can't see infrared, but it's there. Okay, it's happening all around. We just can't see it. How cool would that be if we could? X-ray vision or something. But there are organisms that do. Insects. Insects use ultraviolet waves to detect on flowers where the pollen is. Again, bad artistic representation, but you can look pictures up online of it. It's really cool. Here's a normal flower. This is how we see it. Okay? Because of insects' use of ultraviolet wavelengths, and they can see it, they see a flower like this. And these little purple things coming off are the patches of pollen that they can see. You can also think of it too, sound waves too. We have a specific hearing frequency that we can hear, whereas bats can hear ultrasound and echolation, and they use that to see and to get around. So rainbows are pretty complicated things, but we have mythologies from the past, but once we started observing and using the scientific method, we were able to see what really happens in a rainbow. And if you think about it, it's still just as cool sounding as a bridge from one island to the mainland and crossing it like a rainbow. Millions of raindrops just providing one color, and it hits you just in the right spot to where you see a beautiful rainbow. So next time you see a rainbow, hopefully you see it a little bit differently. And now when you go out and about too, you'll start realizing that there are so many other things that are happening outside that we just can't see. But it's still just as cool. All right, so thank you for listening, and I'll be back later with my lesson plan that I'm going to be doing for my New York City Teaching Fellows interview. I'm going to be working on that today because I don't have to work. So I'm just going to pump some stuff out to prep because my interview is exactly 1 week from today. And I want to do well because I just want to teach. So, all right, thank you. You guys have a good day. I'm going to enjoy the beautiful weather outside. See you soon.